Good afternoon, everyone. Welcome back once again. Now the session will be taken by Miss Anindya Bharatee, Research Scholar, NIT Rourkela, on the topic Power Management Scheme in a PV Integrated Hybrid AC/DC Microgrid. Miss Anindya Bharatee received BTech degree in Electrical Engineering from Government College of Engineering, Keonjhar, Odisha, India in 2015 and MTech degree in Power System Engineering from V. Surendra Sai University of Technology, Burla, India in 2019. She is currently continuing her PhD at National Institute of Technology, Rourkela, India. Her research interest includes design of power management schemes and control techniques of hybrid AC/DC microgrid, grid integration of renewable energy systems, and electrical vehicle charging system. Now I invite Ms. Anindya Bharati to address the session.
Thank you, Pragya, for this nice introduction. I am really grateful to the coordinator of STEM 2023 for this opportunity. Now, the today's discussion topic is power management scheme in a PV integrated hybrid AC/DC microgrid. So, during this discussion, we will go through these points. First, we will go what is sustainable energy, what is the requirement of sustainable energy, and what is the concept behind the microgrid. Then we will discuss the necessity of a power management scheme in a microgrid system. Then we will go what is the system we have taken for this simulation and experimental work. Am I audible? Am I? Can't. Okay. Now am I audible? Then we will go for the different power management algorithm that we have implemented during this work. Then we go for some simulation results and hardware results. Then we will visit the lab for this implementation of this power management scheme. So as we know that because of the growing population and the advancement of technology, the demand for electricity is increasing day by day. So to overcome this increasing demand for electricity and also to reduce the greenhouse gases and the losses due to the long transmission lines, we are now give more emphasis to the integration of renewable energy sources with our conventional grids. Basically, a microgrid concept came from these things. So basically, a microgrid is a controllable power supply system that interconnects with a group of distributed energy sources and loads in a defined electrical boundary. So this microgrid technology gives some benefits like sustainability, efficiency, reliability, robustness, and some power quality features are enhanced in the system. So for in our work for the point of reliability and sustainability, we will consider the solar PV system as renewable energy sources. Also, it has some advantages like low cost, high efficiency, and low maintenance cost and high consistency. But as we know, the power generated from the PV system is dependent on the environmental condition. That is, when there is a change in temperature, when there is a change in irradiance, and it has some effect of on partial shading, humidity. So the power generated from the PV system is not constant because of this environmental operating condition. So that will affect the connected load, that will affect the stability of the system. Hence, to overcome this type of instability, we'll go for the integration of some storage devices. So in this work, we'll consider a combined storage units that we have already discussed, that we have taken both battery storage devices and supercapacitor storage devices. So we integrate both storage devices as a composite energy storage devices. As now here also we have considered the grid connected AC/DC hybrid microgrid. So now we have already connected the PV system and the hybrid energy storage system with some both AC loads and DC loads and the grid. So for the efficient and reliable operation of these components, we need some power management techniques. So now we'll discuss what is the main requirement for these power management algorithms in a microgrid. First, we'll go for load balancing, as there are different types of loads are connected in the system. So we need some optimized distribution of the power among the various loads so that we can prevent overloading of certain components. Then we'll go for an, energy optimization. As here we are using some renewable energy sources, so we need to utilize that renewable energy sources in an optimal way, so with maximum energy cost. Then we go for demand response. When we are connected, when the system is connected with some non-critical loads, at that time we can change the timing of that load by taking the consideration of real-time electricity prices or grid conditions. Then we, as here we have connected the hybrid energy storage system. So the control of charging and discharging of this storage system is mainly dependent on the power management algorithm, so that we can avoid the excess charging or deep discharging of the storage units. This depends on the availability of generated power and the amount of load requirement in the system, and also the state of charge of the energy storage units. Next, as the microgrid can be connected in on-grid, can be operated in on-grid mode and also in off-grid mode. So, when the grid is available in our system, it is called on-grid mode, and when the grid is not connected to the system, it is called off-grid mode. So, the transition between on-grid to off-grid mode should be smooth. So, for this, for this situation, the power management should handle this situation. Then the scalability and flexibility. When we add some extra energy sources to the system, or we add some loads or storage devices to the system, or we remove some sources from the system, at that time our control algorithm should be that much robust that it can handle that situation for sudden addition or for sudden removal of some sources in the system. Then we go for forecasting and prediction. For renewable energy generation, if we accurately forecast the amount of power generated from a renewable energy sources system, then we can go for the rule-based power management technique, and also we can predict the amount of load connected to the system. Now the last point is the fault detection and isolation. Suppose there is some fault in certain areas, or there is some equipment failure. At that time we have to disconnect that part of the system from the healthy part, so that the power supply to the healthy part will not be affected. So these things are the main requirement for a power management system, power management of a microgrid. Now, considering this the necessity of power management, here we have considered a DC bus signaling power distribution scheme to overcome the disparity between the generation and demand, and to enhance the transient power handling capacity of the microgrid. Here we are utilizing one composite energy storage devices, that is the hybridization of both supercapacitor storage units and battery storage units. Then for sharing of power between the battery and supercapacitor, here we have taken one simple filter based control technique, and also that power management algorithm maintains the state of charge of battery and supercapacitor within the predefined limit to avoid the excess charging and deep discharging of the storage units. Also, when there is sudden addition of some sources or removal of some load, at that time there is some power fluctuations occur in the system. So during those conditions, the voltage overshoot and undershoot, the settling time, and the total harmonic distortion of the system is improved by utilizing this power management technique. And finally, those control control algorithm that we have discussed has been verified by using both MATLAB simulation results and both MATLAB simulation results and experimental results. So this is the total system architecture that we have considered for this study. Here PV is taken as a renewable energy sources and it is connected to the system through a DC-DC boost converter. And this is the utility grid. Here I have considered a single phase utility grid and it is connected to the system through a AC-DC bidirectional converter. And both the storage units are connected with the grid, with the rest of the microgrid through their respective DC-DC bidirectional converters. And this is the control algorithm where we have dumped the power management scheme to generate the reference current for these units. And here in a boost converter, the switching of the boost converter is controlled by this MPPT technique. In case of grid connected system, we always run the PV at maximum power point. But what happened in case of DC microgrid? One case arises when PV generation is more and both the storage devices are completely charged. At that time, we have to reduce some power from the PV. So for that, we have to go for off MPPT mode of operation. But this situation will not come in case of hybrid AC-DC microgrid. When there is some extra generation of power, that power will be taken by the grid. So, and in opposite case, in DC microgrid, one case arises that is load shedding when the PV generation is less compared to the load demand and our both storage units are completely discharged. At that time we are bound to set some load, that is the load shedding case, but in grid connected case that case will not arise. At that time this utility grid will supply some load to supply some power to the load. So for bidirectional flow of power, we have connected here one bidirectional AC-DC converter. So here the boost converter is controlled by this MPPT control technique, and the grid controller and the supercapacitor controller and this battery controller are controlled by this power management algorithm. For these control techniques, here we have generated the reference current for grid, reference current for battery and reference current for supercapacitor. And by comparing this current with their respective actual current, we generated the PWM signals for this connected switch. So to achieve a power balance in a system, the difference of power between the generated PV power and load power should be supplied by the composite energy storage system and by the grid. So for that we can write the power balance equation as shown in equation 1. The sum of PV power, grid power, battery power, supercapacitor power should be equal to the load power. As here we are considering the DC bus signaling method. So here we have taken the deviation at the DC bus. This is the deviation at the DC bus. In case of microgrid concept, one of the main requirement is the maintenance of constant DC bus voltage. So from that deviation, we can calculate the total current requirement in the system and we can proceed for the power management algorithm. So here we can see that by subtracting the actual DC bus voltage from the reference DC bus voltage, we can calculate the deviation at the DC bus voltage. Then by using a voltage controller, which is nothing but just a simple PI controller, we can calculate the total current in the system. So as we know, battery can take the average current required in the system and supercapacitor can take the transient current in the system. So for that extraction of average current from the total current, we are using one low pass filter here. Here omega c is the cutoff frequency for that low pass filter, and that amount of average current required in the system should be supplied by both grid and battery units. So here simply we use one low pass filter to extract that average current. Then how we divide the average current between the battery and grid? So for that we have considered one sharing coefficient, that is lambda. So this lambda is decided by considering the state of charge of battery in the system. So battery will take the lambda amount of total average current and the grid will take 1 minus lambda amount of total average current. So accordingly, when after deciding this lambda value, we can generate the reference current for battery and reference current for grid. So here I have shown the logic for that for the calculation of lambda value. Here we can see when the state of charge of battery is greater than 70% or 0.7, at that time lambda value is 1. That means at that time during this operation, battery can supply the total average power to the system and we cannot take any power from the grid unit. Similarly, in opposite case, when the battery SOC is less than its lower limit, that means that battery is completely discharged. At that time, lambda is set to 0. That means battery will not supply any power to the system and grid will supply the total average power requirement to the system. So in this way, we can share the power, average power between the grid and the battery units. Then we come to the supercapacitor units. So for supercapacitor units, the supercapacitor unit can supply both transient power demand to the system, also the uncompensated battery current. So this part will give us the transient power demand to the system and this part will give the uncompensated battery current to the system. By adding this part, we can enhance the transient power handling capacity of the system. So as previously we have discussed, PV will always run at MPP point during grid connected PV system. Then by considering the difference between the generation and load, we can go for two mode of operation. One is sufficient power mode when the PV generation is more than the load, and one is insufficient power mode when the PV generation is less than the required load. So depending on the generation and load, we consider two mode of operation. So now we go for sufficient power mode. So for sufficient power mode, we know that the PP generation is more than the load. So during that condition, we can go for we can differentiate two mode of operation. That is, one is battery charging state, and another one is grid power absorbing state. So what happened when we are going for battery charging state? At that time, we consider that battery SOC is less than its upper limit. That means battery can take power for its charging. So here we can see that the battery reference current is its charging current only. And for grid power observing case, here we consider battery SOC is greater than its upper limit. That means battery is completely charged. So battery cannot take the extra power from the system. That's why we make the battery reference current as 0. And again, we know that supercapacitor is having fast charging and fast discharging capacity. So here we consider both cases. Also here we consider both cases. So when supercapacitor SOC is less than its upper limit, at that time it will take power for its charging, and whenever it is required in the system, it can supply the transient power to the system. And when it is completely charged, at that time only it can supply the power to the system, and we stop the charging of the supercapacitor unit. Similar case will happen in grid power absorbing mode. And respective grid currents, reference grid currents are generated from the power management algorithm. Now we come for the insufficient power mode. For insufficient power mode, the PV generation is less than the load power. So the amount of extra power required in the system should be supplied by the storage units and by the grid units. So here we consider two mode of operation. One is battery discharging state and another one is grid power delivering state. So in case of battery discharging state, Battery SOC is when up to the time battery SOC is greater than its lower limit, battery can supply the lambda amount of average power. So here we can see that this amount of power will be supplied by this battery. When battery is completely discharged, that means when battery SOC is less than its lower limit, at that time we make it to zero, so that battery cannot supply the power to the system. This is done to avoid the deep discharging of battery. And similarly for supercapacitor, when it is greater than its lower limit, at that time it will supply the transient powers to the system. When it is completely discharged, at that time it will not supply any power to the system. And when supercapacitor SOC is less than its lower limit, the transient power should be supplied by this grid. Here we can see that along with the grid reference power, we have added this amount of transient power from the grid. Similar case will be there in grid power absorbing state, power delivering state. Now we'll come to the simulation results. So in figure 2, we can see that from 0 to 6 second, the power from PV, that means the generation is more than the load. Here we have considered both AC load and DC load. So battery, this one is the battery power. As battery power is negative, that means it is in charging state. So during 0 to 6 second, the PV power is more. So during this time, the battery is in charging condition. So after 6 seconds, when we increase the load power, DC load power, at that time, as here we can see that the PV power is less compared to the load power. So battery comes to the discharging state. But here we can see now the battery power is positive. That means battery is in discharging condition. And also from 2 to 4 seconds, we can see one case that here we decrease the PV power up to this amount of PV power is decreased during 2 to 4 seconds, and that extra amount of power required by the load should be supplied by this grid unit. Here we can see that when the PV power is decreased, the grid power is increased to compensate that amount of power to the system. Then during these conditions, we have checked the DC bus voltage. As we know that we have to maintain the DC bus voltage at 100 volt. So when there is a change in PV power at 2 seconds, we can see here only a 2 volt of deviation is there, which is within the limit. According to the IEEE standard 929, it is within the limit. And then at 4 second, when again we increase that PV power, uh, the DC, there is a deviation of approximately 1.5 volt of deviation in DC bus voltage. So that is also within the limit. Again, when we increase the load at 6 second, here we can see there is around 3 volt of deviation in the DC bus voltage. So the voltage overshoot and undershoot are within the permissible limit, and this will take only 0.1 second or 0.2 second to come back to 100 volt. Now here we have checked the grid current and grid voltage, that from 1 to 1.2 second. During 1 to 1.2 second, grid power is positive. That means grid is supplying some power to the system. So during this condition, during this time, we can see that the grid voltage and grid current are working at unity power factor. Then we check the THD of the grid current for 5 cycle. So here we can see that the THD is 1.11%, which is less than 5%. According to IEEE standard 519, the THD of the current should be less than 5%. So it is 1.11%. That means it is within the limit. Now we come to the insufficient power mode. So here we consider two mode of operation. One is the battery discharging state, and another one is the grid power delivering state. So here we can see from 0 to 4 second, the SOC of here from 0 to 4 second, the SOC of battery is greater than its lower limit. So here this graph is the power for battery unit, and this is positive. So it is in discharging state. Again at 4 second, the battery the battery is completely discharged. That means the battery SOC is less than its lower limit. So the battery power comes to 0. At this point, the battery power comes to 0. And when the battery power comes to 0, that amount of power is supplied by this grid. Here we can see after 4 seconds, this grid power is increased by this much amount of power. Then so here we can say this from 0 to 4 second, it is the battery discharging condition, and from 4 to 8 second, it is the power grid power delivering state. And here during these conditions, we have considered constant PV generation, constant DC load, and constant AC load. And also here we can see that at this point, the transient power is handled by the supercapacitor unit. So during this condition, we have checked the DC bus voltage, and there is only a 0.5 volt of deviation at the DC bus when the state changes from battery discharging state to grid power delivering state. Now we will discuss about the sufficient power mode. So for sufficient power mode, there are two state of operation. One is the battery charging state, and another one is the grid power absorbing state. So from 0 to 4 second, it is the battery charging state. Here we can see that, and the PV power is more compared to this load power. So the battery will get some extra power for its charging. So from 0 to 4 second, we will consider that the battery SOC is less than its upper limit, so that battery can take some power for its charging. So here we can see battery power is negative. That means it is taking power from the system for its charging purpose. Then from 4 to 8 second, that is from 4 to 8 second, battery is completely charged. That means battery SOC is greater than its upper limit. So for this case, now battery current comes to 0. Here we make the battery charging current as 0, and the extra amount of power available in the system is supplied to the grid. Here we can see that previously the grid power is positive. That means grid is supplying some power to the system, and after 4 seconds, when battery is completely charged, the grid is taking power from the system. That's why this power is now negative. Then for this condition, we have checked the DC bus voltage, and here we can see there is a deviation of around 3 volt at the voltage at the DC bus during the change of mode from battery charging state to grid power absorbing state. So for this condition, we have checked the frequency of the grid. As in India, we have considered 50 Hz of frequency. So when there is a change in the system, here we can see that only 0.05 Hz of change in frequency is there in the system. So now we come to the experimental setup. As we know that we can directly, here I have taken the DSpace 1103 as a controller. As we know that we can directly connect the external power devices to this DSpace. So for that we need some regulated DC power supply and some sensor circuits. So for this, first we use some voltage sensors and current sensors to step down the voltage and current, because this DSpace will take up to plus minus of 10 volt of voltage. So we have to convert the voltage up to plus minus 10 volt of range, and also the current from some ampere, like from 5 ampere or 10 ampere to within this range. So for that we are using both.
Sorry to interrupt. We want 5 minutes break. The meeting will resume after 5 minutes. I request all the participants to join the main meeting. Please don't start new meeting by your own. It's creating unnecessary confusion. And the main meeting is already started. The session is already started in the main meeting at 3:15. So now the session is again resumed.
Am I audible?
Yes, you're audible.
Okay. Now we'll discuss about the experimental setup, how we implement this power management algorithm in our hardware integration. So as we know that here we are using the DSpace 1103 as a controller. So we can directly give the 10 volt supply or 15 volt supply or some 100 volt and 230 volt supply to this DSpace. It will only take the voltage in the range of plus minus of 10 volt. So for that reason, we'll require some sensor circuits. So there are voltage sensors and current sensors. That voltage sensors will step down the voltage from the rated voltage to plus minus 10 volt, and that current sensor will step down the current from 5 ampere or 10 ampere from some ampere of current to the plus minus 10 voltage of volt of range. Then for operation of this sensor circuit, we need a supply of plus minus 15 volt and ground. So for that generation of plus minus 15 volt, we go for some regulated DC power supply. So for this case, we are normally in our lab, we are using 7815 and 7915 regulated ICs to generate plus 15 volt and minus 15 volt of supply. Then the PWM signals generated from this DSpace will be given to this switch to the switches of this converter. But before giving that signals to the converter, we need some circuits. Like this DSpace will give a the PWM signals that is in plus and minus of 5 volt. But these converters will take the signals in plus minus of 15 volts. So for that we need some level shifter circuits. So this level shifter circuit we will convert the plus 5 volt of PWM signals to the 15 volt of PWM signals. Then before that, here we are using one isolation circuit. What is the need of this isolation circuit? Here we are considering some optocoupler. That is, as we know, this DSpace part is the low voltage part. That is, it is only it will work on 10, plus minus of 10 volt. But this converter part is the high voltage part. We can directly give power to the give the voltage and current to this converter, that may be 30, that may be 100 volt, 200 volt, like this. And so for that we need some isolation between this low power electrical part to the high power electrical part, because compared to this converter, this DSpace is very high cost. So for protection purpose, we will need some isolation circuit. In isolation circuit, I am using 6N137, which is using an optical isolation. Here there is no electrical connection between this DSpace and this converter. So as we are using one optical isolation, so for that, if there is any fault occur in converter side, that will not be affected, that will not reflect to our DSpace. So our DSpace will be in safe side. So this is the total system configuration for interfacing of our physical system to our DSpace controller. Now this is the total laboratory setup that we have developed in our lab for this hybrid AC/DC microgrid. So here this is the host system from where we can control the system, and this is the DSpace 1103. Then for hybrid storage system, as we are using both battery and supercapacitor, these are the supercapacitor units and these are the battery units. And for PV source, in our lab we are using the PV simulator. And these are some sensor boards that are required for this step down of voltage. And this is the R load that we have considered for DC load. And for grid connection, here this is the auto transformer. Here we can regulate the voltage from 230 volt to the according to our requirement in the system. Then for this auto trans, there is one isolation transformer which is only for the protection of the system. Then this is the AC/DC bidirectional converter which is connected to the load. Then for a nonlinear load, here we are considering a diode bridge rectifier and one series combination of R and L is connected across the diode bridge rectifier for nonlinear load. So this total part is the nonlinear load part. And here we are using one MCB to connect the grid to the system and also to disconnect the grid from the system. This is only for grid connection and disconnection. We are using one MCB there. Then we come to some experimental results. So here we consider that the difference between the load power and PV power is taken as PR. So this PR, here we are showing this PR value. So here from 0 up to T1 second, before T1 second, the PR is negative. That means the PV generation is more. So as the PV generation is more, here we can see that battery power is negative. That means battery is in charging condition. During this condition, we have considered constant PV voltage and constant DC power and constant AC load power. So here we can see that the battery is in charging condition. Then at T1 point, we increase the AC load power. We increase the AC load power here. So as we increase the AC load power at this point, so this PR value becomes positive. So here we can see that the PR is previously the PR value is negative and at T1 point it is positive. That means previously it is working in sufficient power mode. Now after T1 point it is working as in insufficient power mode. So to compensate that amount, to provide that extra amount of load power, the battery, previously it is in charging condition, now battery comes to the discharging condition. Here we can see the transition that battery, previously battery is in charging condition, now this battery is in discharging condition. So now we come to the change in load, change in PV generation. Previously we have shown how the system will behave when there is a change in load. Now we'll see how the system will behave when there is a change in PV. So here we can see that the DC bus voltage is 100, which is maintained throughout the operation. So before T1 second, the PR value is negative. PR is negative means generation is more. So as generation is more, battery is in charging condition. Here we can see that the battery power is negative. That means battery is in charging condition. So suddenly at T1 second, we reduce the PV generation. Here we reduce the PV generation. As the PV generation is reduced, so the PR value will increase. So it comes to positive value. So during this condition, as the PV generation is reduced, the battery is changing from battery charging state to battery discharging state. Previously, it is in negative power. That means the battery is in charging state, and now the battery is in discharging state as this is the positive battery power is there. And throughout this condition, as grid power is positive, here also it is positive and here also grid power is positive. So it is in grid delivering power mode. Now, another one of the main requirement of a hybrid AC/DC microgrid is to operate the system at unity power factor. Here we can see that the battery grid voltage and grid current are operated at unity power factor. Because of the operation at UPF, we can reduce the transmission losses. Also, we can improve the voltage stability so that the extra compensation techniques are not required in the system. And also for renewable energy integration, it is required so that it will seamlessly we can integrate the renewable energy sources to our grid. Now we come to the conclusion. Hybridization of supercapacitor with battery can extend the lifetime of the battery by diverting the high frequency current to the supercapacitor units. And the proposed control energy management performs the main function of a bidirectional linear power flow between the utility grid and the microgrid. Whenever there is excess power in the system, the grid will take the power. When there is a deficit power in the system, the grid will supply that amount of power to the microgrid. So as here we are considering the DC bus signaling scheme by comparing the actual DC bus voltage with the reference DC bus voltage. So you can see there is very less voltage overshoot and undershoot in our DC bus during any changes in the system. That means when we are changing the load or when we are changing the PV power in the system. And also in the previous slide, we have seen that the system is always operated at unity power factor, which reduces the losses and harmonics in the hybrid AC/DC microgrid. Also, it improves the voltage stability without any extra compensating methods, and it provides the optimal utilization of the renewable energy sources. And fast restoration of DC bus voltage is there, as our settling time is very less in different operating condition. Also, it keeps the HOC of the storage devices within the limit, so that it can avoid the excess charging and deep discharging of the storage devices. And finally, we verified our proposed technique by using both MATLAB simulation results and experimental results. For more clarification regarding these techniques, you can go through these references. And thank you. If anyone has any questions, you can ask.
I request participants, if any query, can ask to madam.
Good afternoon, ma'am.
Yes, good. Yes, good afternoon.
Then how we are going to reduce the settling time in power management, ma'am?
What?
Settling time.
Settling time. Actually, when here I have not shown you the settling time, but here we can see that in simulation results, here we can see that when there is a change in the system, there is a deviation of around 3 volt in the system in DC bus, and it will come to 100 volt again after 0.1 second or 0.15 second. So that 0.1 second or 0.15 second is the settling time of the system. Accordingly, we decide we measure what is the settling time in the system from these graphs.
I mean, is there any technique, I mean, like a FLC and ANN, can we use a further reducing of the settling time?
Okay, actually, our power management scheme is that much robust that our automatically it will reduce that settling time. We have not added any extra features to reduce the settling time, because we are going for a DC bus signaling method. So when there is a deviation that is as shown in equation 2 or equation 3, from that deviation we generated the reference current. So from that deviation, as we generate the total power management algorithm, so that will automatically handle these settling times. And because it will always try to maintain that 100 volt of the DC bus voltage.
And one more question, ma'am.
Yes.
I have doubt that, I mean, at what percentage will take the capacitor and battery in power management, ma'am? And it is initially it will take power capacitor or in middle or simultaneously it will take, ma'am?
You just repeat the question.
Capacitor and supercapacitor and battery is there, man, power management.
Yes. Yes.
Depending upon the SOC, it will take, or depending upon the requirement, it will take. I mean, yes, supercapacitor gives the transient, and where the battery gives the average power. On what base it will take the percentage of those energies, ma'am? given instant.
Okay, actually here we consider both the cases. Suppose when there is sufficient power in the system, that means when the PV generation is more than our load requirement in the system, at that time we have some excess power, excess PV power in the system. So during that case, we check whether our storage units are completely charged or discharged. Our first aim is to take the difference between the load power and generation. If generation is more, then we will go for the SOC of battery and supercapacitor. If they are not completely charged, then we provide that extra amount of PV power to the storage units for charging. Similarly, in opposite case, when the PV power is not sufficient, at that time we check whether our battery and supercapacitor SOC are greater than their lower limit or not. Because when they are greater than their lower limit, they have some charge, they can discharge power for the to supply the loads. So during deficit power mode case, we take some power by checking the SOC of the storage units only. We check both power and SOC for charging and discharging of the system.
Is there specifically advantage supercapacitor? Otherwise, I want to remove the supercapacitor at that time. Two batteries I'm using. Then is there an advantage, ma'am?
Use of super, is there any advantage of using
Supercapacitor.
supercapacitor? Okay, like in the previous in the first day session, that Professor Rai sir has taken one class and he has shown some graphs when we are using the supercapacitor and when we are not using the supercapacitor. What is the effect of battery current? That when we are using the supercapacitor, the transition of battery current is smooth. And when we are not using the supercapacitor, at that time there is a sudden transition of battery current that will affect the battery power, because battery is having high energy density. It can handle average power for a longer duration, and it is having slow charging and slow discharging. But in case of supercapacitor, it is having high power density capacity, so it can go for sudden charging and sudden discharging. So if we take some transient power from the supercapacitor, it will not affect the life of the supercapacitor. But if we will take that transient power from the battery, it will affect the life of the battery, because it is having slow charging and slow discharging. So for that, to tackle this situation, we are going for the hybridization of both battery and supercapacitor.
Thank you, ma'am.
Okay, welcome.
Any more questions? Okay. Then moving forward, we are taking here 5 minutes break, 15 minutes break. Then we will resume with the lab visit. Let's resume. Now it's time for lab session. Miss Anindya Bharatee is going to demonstrate the developed experimental prototype of hybrid AC-DC microgrid. So it's over to Anindya.
Yes, now am I audible?
Yes, you are audible. Yes.
Okay. This is the total lab setup that you have seen from the screen. So here we can say that this is the DC-DC converter for this super capacitor units, and this one is the DC-DC converter used for this battery units, and these are the sensor boards that is used for the interfacing of these converters with their D-Space 1103 controller. So this is the D-Space 1103 controller, and here this is the isolation transformer that is used for the isolation of the total microgrid from the utility grid, and this is the sensor circuit that is used for this specially for this utility grid. And this one is the hybrid. This one is the AC/DC bidirectional converter that is used for the bidirectional flow of power between the battery, between the grid and the rest of the microgrid. And these four are the battery units. Each one is having 12 volt and 42 ampere hour. Here I have connected four in series. That is, each one is having 12 volt. So there is total of 48 volt, and each one is having 42 ampere hour of capacity. Then for nonlinear load, here I have considered this diode bridge rectifier, and and this is connect and this is connected across this resistive load and that inductive load. This resistive load and inductive load are connected in series, and the combination of the series combination of this R and L is connected across this diode bridge rectifier for the nonlinear load connection. Then here this is one small voltmeter, which is from this voltmeter we can see the direct the DC bus voltage directly from this voltmeter. And here it is the resistive DC load which is connected across the DC bus. And this one is the PV simulator. Here we are using using one PV simulator instead of direct PV source PV panels. So here this is the PV simulator, and as we know that PV is connected to the rest of the microgrid through a boost converter. So this converter is specially for this PV simulator, and this one is the boost converter, and these sensor boards are for this PV system. This is the total system for PV unit. Then this one is the power analyzer. By using this power analyzer, we can see the voltage and current. We can check the TSD, and we can check the peak values and RMS values. All those things from this power analyzer. Here I have only taken the grid voltage and grid current. I have checked only the grid voltage and grid current by using this power analyzer. So this is the D-Space 1103. D-Space 1103. Here there are 16 ADC channels and 8 DAC channels. By using these ADC channels, we have given the sensing voltage and current to the D-Space. And by using these DAC channels, we have taken we have taken the sensed current and voltage to check it by using the DSO. As I am having only a 4-channel DSO, so I have taken only 4 DAC channels to check those values. Now then this is the slave IO input IO. So by using this slave IO, I have taken the PWM signals which are generated from this from this dispatch unit. Then after taking the PWM signals, I have designed the isolation circuits and level shifter. Then after that, I have given those PWM signals to this inverters for switching of these inverters. Now this sensing board will measure the DC bus voltage and the DC load current, and this sensor board will measure the nonlinear load AC load current, the grid current, and the grid voltage. So from this power analyzer we can see that now the system is in running condition. Is in running condition. Here we can see that as one of our main requirement is the operation of grid voltage and grid current at unity power factor. So from this power analyzer we can see that our grid voltage and grid current is at unity power factor. Then from this DSO also we can see these values from this control desk screen that our DC bus voltage is maintained at 100 volt, and these are the three supercapacitor units, and these units are connected to the system through this DC-DC converter. So from this DSO also we can check that this fast channel is connected to show the DC bus voltage. Here we can see that this is the DC bus voltage which is maintained at 100 volt. As we have already shown in simulation results and also in experimental results. So this is maintained at 100 volt. And the second one is the PV power. So we can change the PV power by changing from that PV simulator units. And also here we can see that third graph is positive. That means the battery, this third one is the battery power. And as this is positive, that means battery is in discharging condition. And this fourth graph is negative. That means the supercapacitor is in charging condition. Because when we start a system, the supercapacitor is always there in discharge condition. So when we start a system, it will start charging initially. After that, it will take the transient power handling. After that, it will handle the transient power. So now the supercapacitor power is negative. That means it is in charging condition, and this grid power is this battery power is positive. That means it is in discharging condition. So here we can see the models, like this is the host PC. So here I am using MATLAB interfacing system. So by using some ADC blocks and DAC block, and I have implemented the control algorithms here. And after completion of this, I just build this model to dump this model into the D-space controller. So this system is there for the control of this control desk. This software is the control desk, which is the interfacing between the D-space and our MATLAB. So if there is no DSO is available in any institute or in any college, so we can directly check the values from this control desk unit. Here we can see that we are checking the DC bus voltage, grid current, and all those powers and voltage across every system. So now we'll check this. This one is the this is the auto transformer, and this is connected directly to the power supply. So by changing this switch, we can change the voltage, AC bus voltage, according to our requirement. And this auto transformer is connected to this isolation transformer directly. Then after isolating this total power supply from our microgrid, this is after isolation. This is before isolation, and this part is after isolation. So after isolation, we have connected it to the rest of the system. So then there is another case arises when grid is connected and grid is disconnected. So for connection and disconnection of grid, we have connected this MCB here, so that when it is off, the grid is disconnected, and when it is on, the grid is connected to the system. And this is the this one is the sensing board for this grid units. So if we want to change some load or change some PV generation, that will automatically reflect in the DSO. So no need to dump or build our program again and again. It will automatically reflect because we have already programmed our system in that manner that when there is a change in load or when there is a change in PV system, then it will automatically handle the total power in the system to balance the power in the system. So here we can now clearly see that the power analyzer is showing the unity power factor operation of grid voltage and grid current. Here we can see that the unity power factor operation of the grid voltage and grid current. So, and this DSO now showing the DC bus voltage. First channel is the DC bus voltage, then second one is the PV power, then third one is the battery power, and the last or fourth channel is showing the supercapacitor power, and these three are the supercapacitor units. And this is the total setup for this power management algorithm. So if anyone has any doubt, you can ask if anyone has any questions regarding this setup.
I request participants, if any query, can ask to Miss Anindya. So no question from audience side. Okay, then moving forward. Thank you very much, Anindya, Bharatee, for such a splendid and informative presentation, giving every minute details of the equipments installed in the experimental prototype while developing the prototype of hybrid AC/DC microgrid, both in running condition also. Thank you very much. So, moving towards to end the session. I'm going to conclude the session here. Tomorrow the session will start at 10 a.m. due to some busy schedule of tomorrow's guest speaker from Sri Lanka, Professor A. Vijayapala. So, so instead of 9:30, it will start at 10. The inconvenience caused is regretted. So thank you for cooperating. And it's a humble request to every participants, kindly join the main meeting. Don't start the meeting by your own, because this is creating unnecessary confusion, and due to this many of our participants are unable to attend the session because they're getting into the wrong meetings. So it's kind request to every participants, please cooperate with us in this. Thank you. I'm ending the session here.